Okay, so good to see that so many of you were able to make it. So I'm going to start off by reviewing the Z transform. And I mean, this is so. I'm going to work through some examples that will hopefully illustrate the concepts and the usefulness of the Z transform. And I'm going to look for. I mean, hopefully you're going to be able to answer some of the questions as I go along, and definitely stop me if there are any questions or confusion or what's going on. So just to recall the formula, I'm sure no one has forgotten, but let me write it here. So if you have a discrete time signal x of n, then you define its Z transform in this way. It's the sum of x of n, z raised to minus n. And this quantity might only make sense for certain values of z. So you have something called a region of convergence, right, where this sum is actually meaningful. It's not infinity. So in class you did a fun example using Laplace transforms to track or to balance this inverted pendulum, right? So so it turns out you can use the Z transform to analyze rabbit populations or populations in general. So so here's example number 1. Due to Fibonacci. Okay, so I'm sure most of you have seen this before. The Fibonacci sequence is where you start with a 0 and 1, okay, and every term after you obtain by adding the previous two. Okay, so 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. Okay, so apparently this was, I mean, he had a model of rabbit populations, and this is given by this sequence. When you start with one rabbit couple, this is sort of the growth that his model predicted. So in terms of recursions, this is just described by y of n. The population at the nth time is the sum of the populations at the two previous times. Okay, that's exactly what the sequence is doing. Now, so just given this recursion, well, we usually talk about Z transforms when you have an input and an output, right? But right here, I just have one sequence. There's just a y here. So so what you might try to do is add an input which would be interpreted as the initial number of rabbit couples that you started with, okay, in your ecosystem, if you like. So I just add that as an additive term here, x of n minus 1. So given such a thing, you can take the Z transform of it. But let's put that off for a second. Firstly, let's try to see what the block diagram for such a thing might look like. So rabbit populations is just an excuse. I mean, we really want to analyze this. So wait, does anyone have any idea how you would design a block diagram, a system for this. So you see that you have yn minus 1 and yn minus 2, right? And y is the output, so it's feeding back into itself. And since you see yn minus 2, you know that you should have at least 2 delays, right, in your system. So I'm in the interest of time, I'm going to give you the system, but you should maybe practice on your own to see if you can go from recursions to block diagrams, because that might be helpful. Okay, so I claim that this is the system, and you can easily check this. So yn is being fed back into the input, so is added to x of n, which is your input signal. So right here you have a yn minus 1, okay, and here you have a y of n that comes in. And then everything gets delayed by 1. So you get yn minus 1, yn minus 2, and xn minus 1. Okay? And so you know, a lot of what you've been doing in the class is, once you have such a system, you want to compute its impulse response, right? So let's just try that by hand. What happens when you have the input? X of n is just delta of n. It's 1 at time 0 and 0 everywhere else. I mean, the output for that is called the impulse response, right? Just by definition. So so y of 0 is just 0, right? Because delta of negative 1 is 0, okay? And I mean, y is obviously 0 for negative time. You had no rabbits in negative time. You introduce a rabbit couple at time 0. So, okay. So is everyone with me? Okay. So time y of 1, you now have y of 0, okay, according to the recursion, and the other two things. Oh, yeah, x of, okay, sure. Y of 0 is 0, but now you have x of 0. That's the important thing. So you get 1, okay. So you can continue this. So y of 2 will just be y of 1, because the other things are 0. You get 1 again. So by now, for y in later time, x has no contribution, right? Because that was just a delta function. So y of 3 is y of 2 plus y of 1, both of which are non-zero. So you get 2, and you see that you're getting the Fibonacci series again: 0, 1, 1, 2, 3. So the impulse response of this system is exactly the Fibonacci sequence. Okay. And now let's see what we can learn about the sequence using the Z transform. Okay. So recall that when you have a signal of time y of n minus k, the z transform of that is z raised to minus k times y of z, and right, and you just get that from definition. But it's completely okay to remember this formula. You don't need to rederive it every time. So for the recursion that we have here, if we take z transform of both sides, what you're going to end up with is y of z equals z inverse y of z, that's y of n minus 1, z transform, plus z inverse squared of y of z plus z inverse of x of z. Okay, and we can write what we call the transfer function of the system, h of z, which is the ratio of the output over the input. So this ratio is supposed to tell you how the system affects inputs. Right? Okay, so it's something that looks like this, and you can go ahead and multiply both numerator and denominator by z squared, and you get something like this. Okay. Now when you have something like this, if you want to understand what the system is doing, you should really try to factor the denominator into its poles. So you can check this. I used you can use the quadratic formula to come up with the roots of the denominator, z squared minus z minus 1, and you can check this yourself. Okay. So so if you draw a pole zero diagram, so we have real part of z and imaginary part of z. So this number is roughly 1.6. This number is roughly 0.6. Okay, so that means you have it's minus 0.6 actually. So so that means you have poles at and you have a single zero, single order zero, right? Because your numerator is z. Okay. So now, just looking at this pole zero diagram, can you describe to me the qualitative behavior of the sequence? So that's what I mean. That's the use of having such a diagram. It's like a concise description of what your system does. So for one, you see that everything is on the real axis, right? So the fact that everything is on the real axis means that your system has no oscillations. So does anyone want to? Does anyone see how the system is going to behave? Is it stable? It's not stable. Why is that? Right. And you're assuming you have a causal system. So that means your region of convergence is everything outside the circle of radius 1.6, right? So it's not stable. Um, um, oh yeah, that's what. So yeah, it's hard to draw circles here, but so right. But what do the numbers 1.6 and minus 0.6 tell you? So roughly it means that you have the rabbit population can be described as a sum of two exponential terms. One of them looks like 1.6 raised to n. Okay, 1.6 raised to n is going to go to infinity as n grows. And the other term is minus 0.6 raised to n. 0.6, since it's less than 1, is going to go to 0, right? And you have a minus sign in there, so there's going to be some oscillation. Just sign flips. So it's kind of neat that you, just by looking at the poles of a system, you can say things about its qualitative behavior. So let's actually go ahead and verify that now. So if you start with the form of h of z in terms of z inverses, so I think it's better to work with this form for doing the exact calculation, just because the z transforms we've provided to you are in terms of z inverse. So if you recall, 1 over 1 minus a z inverse, the inverse z transform of that would go to a raised to n u of n, right? And you need right. Your region of convergence is magnitude of z greater than a. Okay, I think that's right. Please correct me if it's not. So you can just treat z inverse as a variable and do partial fraction expansion on that. So So I actually did it at home, but you can verify that. So does everyone know how to do partial fraction expansions? You should definitely practice it. It'll be useful for your final exam. I don't know if you'll use it after that, but yeah, for the final exam, definitely practice partial fractions. So we can. And now you see we have things of the form 1 over something minus z inverse, right? So we can just look up our table of Laplace transforms. But let me do one more step and rewrite this as Okay, and since the system is causal, we know we have a region of convergence that's z greater than 1.6. So by the formula we have here, the inverse Z transform formula, in time the impulse response looks like h of n is 1 over square root 5 so this is the constant a that is an exponential. Okay, this is just coming from this formula, right? So you don't need to do any computation. Once you get it in that form, it's just a lookup. Okay, and I can factor out a un over square root of 5. And you can rationalize the denominator of this. It's I'm sorry. Okay, so you see we have this nice looking form. The first term here is a number that's greater than 1. It's like 1.6 raised to n. The second term here is minus a 0.6 raised to n. So exactly what we predicted from the pole zero diagram. So this is somewhat exciting, not extremely. So as n goes to infinity, asymptotically, the minus 0.6 raised to n term, that's just going to go to 0. That's going to die away. So your rabbit population is going to be described by phi raised to n. So over square root of 5. So this number here is actually famous. It's called the Golden ratio. Phi is 1 over square root of 5 over 2. Okay, so just using Z transforms, you could analyze a sequence of a purely combinatorial nature. You just had some recursion and you wanted to know how the sequence behaves as n grows large. And here we have an exact characterization. Okay, and yeah, this number comes up all over the place. Golden ratio in sunflowers and rabbits and everywhere. Okay, so so this is an example where your system, well, the impulse response displayed pure exponential behavior. So both your poles were on the real axis. Okay, no imaginary component. So I mean, there was no oscillation except the sign flip due to minus 0.6. But I mean that vanished. So, but this is not the only qualitative behavior that you can expect, obviously. So let's do an example where you have purely oscillatory behavior. So whenever I write down a formula like this, the y of n output is equal to some function of the input. I mean, you can already tell if it's a causal system or not, right? So then, if I give you the pole zero diagram, and I give you this formula, then you know what the region of convergence is. Because if it's causal, then it can have no outer boundary. Okay. So, I'm sorry? At rest? What do you mean at rest? There's no initial condition here. It's just a recursion. It's just a difference equation. There's no initial condition. Okay, so again, since we're doing the Z transforms, we take the Z transform of both sides. And you get that the transfer function is this guy. Okay. So in terms of block diagram, the system is very simple, but it's just meant to convey a point that you can have your impulse response can be of a purely oscillatory nature. So what you're doing here is you're just taking your output, delaying it by 2 time seconds, by 2 seconds or 2 time periods, whatever. And some people write that as 1 over z squared because delaying is 1 over z. So this is pretty common notation to write 1 over z squared for 2 delays. And then you add it back into x of n. Actually, you negate it and then you add it. So you subtract it from your input. Okay, that's what the system is doing. And just by looking at this diagram, you should be able to see what the impulse response is. So if x of n is just a delta function, you send it a 1 at time 0, then 2 seconds later it's going to come back as -1. 2 more seconds later it's going to come back as +1, and so on. It's going to keep coming back every 2 seconds with the sign flip. Right? That's only if you ping it with a delta function at time 0, because you're not doing anything else. You're just delaying it and changing its sign. So this has poles at plus and minus I, because z squared is z plus I times z minus I. And you have a 0 of second order at the origin. So okay, so is this system stable? So it has poles on the unit circle, because I and minus I are on the unit circle, right? So is it stable? So it's not stable, because if you recall, the criterion for stability is that the unit circle must lie strictly within the region of convergence. But here, the unit circle is on the boundary. So this is the unit circle, and your region of convergence is, since it's causal, you know it has no outer boundary, so the region of convergence is all z's with magnitude greater than 1, right? But that's your boundary, and you have poles lying on the boundary. So you can cook up, I mean, if you, for instance, if you input a unit step into the system, which is ones for all positive time, then or I think you need to do like a +1 -1 +1 -1, so that the minus ones just cancel with the negation, and then you get some sort of positive feedback. But you can, yeah, it's more of an yeah, it takes more work to come up with examples, but just by looking at the pole zero diagram, you know when the system is stable. So so just to write down what we already observed, the impulse response is just going to be a 1 up to sign flip on even times, and 0 on odd times. Okay, that's just because we have a delay of 2, so you're only going to see a 1, you know, at even times. Okay, so this is pure oscillation. Your poles were imaginary, so it's just oscillation, and it's you also, so note that I and minus I are in angle. It's a quarter of a full rotation, right? And the period of the impulse response is exactly 4. That's the time between two consecutive ones is 4, right? Because you see 1 0 -1 0 1. So that's another thing you could tell just by looking at the pole zero diagram. But the phase of the poles, you know what's the frequency of the impulse response. Okay, so so remember that we're treating a complete revolution around the unit circle as going from 0 to 1. So if you go a quarter of the way, you go to I, or minus a quarter goes to minus I. Okay, so here's a question for you. Okay, is this a causal system? The transfer function is z squared plus 1 over 3z. Is it causal? I see a no. Does anyone else have an opinion? Could be. So why do you say it's not causal? The numerator has a higher order than the denominator. So I think what she's saying is that you can write this out as z over 3 plus 1 over 3z, right? Okay. And if you do the inverse z transform of this, you get 1/3 times delta of n plus 1 right? Because the Z transform of 1 is just delta of n. So Z transform of Z times 1 is delta function shifted, right? Plus 1/3 of delta of n minus 1. Okay. And you see that for n equals minus 1, this thing is 1. So it's not causal. For causal, you need it to be 0 for all negative times. Okay. And so we saw two examples, one of which you had pure exponential growth, that was the rabbit population, Fibonacci, and the other one was purely oscillatory growth. But I'll just point out that you can also get polynomial growth, like you could get n squared, and so on, for higher order poles. So it's unlikely that you'll come across this, but I'm just letting you know that you can describe more interesting kinds of systems. So, okay, but you can find that in your notes, so I won't write it here. How are we doing on time? Okay, maybe I'll do this example, and then maybe we can switch, unless you want me to do Laplace transform also. No, I'll do it if you're good on time. But well, we have to be reasonable. Okay. Oh yeah, feel free to ask questions. You don't need to wait for the question session. You can ask questions. Okay, so let's just do another example where you start with the pole 0 diagram. So you have poles at 0 and half, and that's all you have actually. This is for x of z, and you're given that x of 1 is equal to 1. Okay, so can you recover the system just given this information? So apparently there's no zeros and just two poles, right? And since I didn't assume they're just first order poles, okay, I would have said otherwise if they're higher order poles. So immediately you know what the form of the Z transform should look like, right? It's just going to be 1 over Z times Z minus a half. Right? Well, you don't know if it's 1 yet. In general, it's going to be some constant k over Z minus half. And I told you that x of 1 is equal to 1. So you can solve for k. So k is apparently minus 2. Okay. Oh yeah, that I just used x, but maybe I should use h. Yeah. No, so I just gave you a pole 0 diagram. Like, I'm not saying where this came from, if it's a system. I mean, Yeah, I didn't tell you anything about H's or X's. Oh, that's right. Yes, thank you. That's great. I was just checking if you're awake. Let's make this H. Okay, so we have H of C. And now, let's say you've been asked to plot the frequency response. Oops. And the phase of the, and its angle, and its phase. So what does it mean when I say frequency response? So usually what that means is you plug in Z equals e raised to 2 pi e raised to I 2 pi f. Okay, and f is your frequency in hertz or bar or whatever. So this means the so this is absolute value of h of z for it's basically on the unit circle. That's what we mean by frequency response. You're on the unit circle and you're changing your frequency. Frequency lies between 0 and 1 for discrete time. Okay, and its phase is obviously just the angle. So one thing we can be sure about is that both of these quantities are going to have period 1, right? Because e raised to I 2 pi f is periodic with period 1. Okay. So for just plugging in 0 into, so we have h of z here. So you might be asked to make a qualitative sketches like this because it sort of conveys the behavior of the system, which frequencies are attenuated, which ones are amplified, and so on. So plugging in z equals 0, you get 1. The amplitude is 1. So it starts here at this point, and actually, you can glean a lot of information just by looking at this diagram. So if you remember in class, Paul mentioned that when you're on the unit circle and you're closer to the poles, you expect the frequency response to be larger. Okay, so you would expect that you have a maximum when you're at this point right here, but when you go halfway around the circle and you're here, you're the furthest from the poles, so you'd expect a minimum there. So we should expect to see some kind of minimum at half, okay, when you're halfway around the circle. And plugging half into the formula, well, oh, sorry, it's in the exponent. So for f equals a half, you would be plugging in z equals I, because e raised to I pi is I. No, is minus 1, sorry. Minus 1. So, okay. So let me just write this out. H of okay. H of e raised to 0 is h of 1. That's wrong, isn't it? It's supposed to be 4. Okay, but okay, so this is not going to plan, but hopefully you can see that qualitatively, just by looking at the pole zero diagram, and you can check me on this. You're going to get a plot that looks like this. You're going to have a minimum when you're halfway around at the point that's furthest from the poles, and then you're going to go up again. So, and you're going to get something that's periodic with period 1. Okay. So this is going to be your frequency response, and similarly you can do the phase. Just note that the phase of h of z is equal to the sum of the phases of the numerators minus the sum of the phases of the denominators, right? Because you're multiplying everything and phases are in the exponent, so they add. So maybe I'll leave that as an exercise since we're running a bit short in time. But I'll just write it here. And in this example, you don't have any zeros, so you just have two poles. So when you start off, when you're at 1, you have negative. So you're making angle. So you're looking at these two vectors, right? So maybe I should. You're looking at the angle made between. By the vector joining the poles with where you are on the unit circle, right? So when you're at point 1, both the angles they're along the real line, so it's just 0 for both of them. Okay. When you reach this point on the unit circle, you can see that this angle is going to be 90 degrees. Okay, for this pole here, but this angle is still going to be like 30 or something. Or 45 degrees. So you can figure this out exactly as you go along the unit circle, how your phase is going to change. So note that when you get here, when you get to I, then you're making an angle of roughly pi over 2 with both the poles, right? It's going to be a bit more than pi over 2 because this guy here makes an obtuse angle with. So you're going to have something that's like negative pi, roughly. Okay, so maybe you should think about that some more. But I'll leave that as an exercise, and you can ask us later if you have questions. What's that? What's that? Oh, okay, sure. So are we do you want me to do one Laplace transform example? Or
No, because you're sort of doing filter. And I have filter.
oh, do you have Laplace transform? Oh, you do. Laplace.
Well, I have Laplace transform filters.
Okay, excellent. So I think you can. Okay. So we'll transfer this to you.
Okay, I have not used this before, so we'll see how it goes. Okay.
Just make sure the mic is.
How do I know if it's working? Is that? Okay. Well, hopefully it's recording this. That would be good. So filters. It changed color. That's good. Okay. So I went over filters sort of in the Z domain. So we'll do one in say, the S, or the Laplace transform. So in this case, this is S. Right, so in the Z case, it's the unit circle that gives us the frequency response. That's the Fourier transform. And in the Laplace transform, it's the imaginary axis, right? It's when so when S is only equal to j omega, that's when we get the Fourier transform. So that's how we convert it from the S to the Fourier transform to get a frequency response. So for the Z transform, it was R, the magnitude was 1. In this case, it's the imaginary axis. So if we have a pole, say here, how do I scroll down?
Oh, using the scroll bar.
Oh, okay, that works. Cool. Our frequency response, if we have some point omega on our axis, we draw a line to the pole or the 0, and the distance here is going to be the gain of our system at that frequency. So gain yes, and this angle here is going to be the phase of our system. So because this is a pole, one over the distance. If it was a 0, it would just be the distance, right? So the pole is the reciprocal. So as we get closer to the pole, it gets higher, as the distance gets smaller. So if we're plotting our gain as a function of f, see, it gets closest, this distance is smallest when we're here at the origin. So when f equals 0, it's the highest, and it decreases from there. So it's similar to what I just did in the Z transform. You can imagine it as, I think the common example is a rubber sheet where the poles are underneath the rubber sheet and pulling it up, and the zeros pin it down. So if you're close to a 0, you have a low gain, and near a pole, it gets higher. So you want to be as close to the poles as possible. And our angle, h minus theta for pole for 0, where theta is our angle. So we can quickly find, say, h of f. If this is a triangle, one side is 1/2, the other side is w. So it's 1 over 1/2 squared plus omega squared. That's our gain. So if you wanted to find it without actually, we could do the same thing. We could write it in the form so we have 1 over s minus 1/2. Then s goes to j omega, and we multiply it by its complex conjugate, and we get the magnitude. Or we can just do it looking at it as a triangle. So this might be a shortcut if you're trying to find the gain quickly on an exam. Make sense? Yeah. What's a triangle? So the hypotenuse equals the opposite squared times the adjacent squared. So this is 1/2. This is omega. So omega squared plus 1/2 squared equals the distance squared, which is our gain. So it's just looking at it. You can see if you're that far away, omega is one side. It's a right triangle. I think this is a little bit faster. And of course the angle is the tan minus 1 of the opposite, which is omega over minus 1/2. And because it's a pole, so there we've got our phase and our magnitude of this filter and a basic plot, and you just can get all that. Like Sai said, you can get a lot of information from the pole zero plots. Yes? Now, let's go over group delay. So I think Professor Cuff went over that, but there was some confusion about which formula we were using. So maybe people didn't understand where that came from. So we gave an equation for the group delay. And we do an example based on the book that I liked, 6.24 from the book. It's the H. So it's a rect. So it tells you that this is the magnitude, and it says group delay equals 5 seconds. What is it erased? So exciting. T. So this is what we're trying to find. So given these two pieces of information, we have the magnitude, and we know the group delay is 5, and we also know when is real. So now we need to find the impulse response from this information. So we say the angle equals so it has some real part and some imaginary. Sorry. No. We still have to multiply it by I. So this is what we're trying to find. So this is our form of the angle. So some part depends on the frequency and some part does not. How do I get a new page?
Oh, you just keep going down. Hit the arrow.
Oh, the arrow, okay. because the scroll bar is at the bottom. Okay. So we know a delay of... This thing is not as easy as it looks. T minus T naught. So a time delay will show up here. Something times the frequency. This means alpha will be our frequency, will be our time delay, right? So in this case, T naught would be alpha. So we have something e to the I this is what we're multiplying our signal by, right? Times some magnitude. Yes. I learned one in one class and one in the other. Yeah. I and J are the same thing. You all know that, right? They're the same thing. So clearly here, T naught is alpha. So T naught equals 5 equals alpha. And because it's a rect will go to a sync. So we will get h of t equals, right, this is a constant. It doesn't depend on the frequency, right? So we can just put it outside the transform, and we get this. So our delay is 5. We have some constant out in front, and we have the inverse transform of our rect function. Yes? And because we know it was real, that was the other part information we had, we know that this equals 1, so this equals 0. So we can get rid of that. So you should be able to get from the group delay and the magnitude to the impulse response. Yes? I know my handwriting is terrible. I'm really sorry. I like Blackboard's better. Can you read it? Kind of? Okay, good. So what we've really done here is said that if we plot this phase, it will look like this. Slope so the slope of our phase is our group delay. So what we did when we said that the group delay as a function of frequency was equal to minus or whichever one you're using. What we really are doing is, I'm hitting the arrow, is we're saying we have some function, our phase, and at every point we said it was approximately a line with some slope. That's why we're taking the derivative, as we're making an assumption that around that point it's a line. And the slope gives us our time delay. And the slope is, of course, just the derivative. So that's why we're taking the derivative to find the group delay. So if we took the derivative of this, we could find the group delay as a function of frequency, which is of that. Yes? I think that's all you need to know about group delay. Yeah, we're good with group delay. So going back to filters, I think Professor Koff talked in class about infinite impulse response and finite impulse response filters. And I need to talk briefly about the difference between the two. So we have some system and this is pretty much the most general system that you'll get. It has both recursion, so we take the output at previous time. This is the same thing. So this block diagram is the same way of saying we have some nth order response on one side. Yes? So this is our general filter design. So to find our poles and zeros, we have h of z equal b naught right? Which will convert to some zeros and poles. So zeros on top. So we have m zeros. And on the bottom we have n poles. Yes, and we can find the gain, we can find the phase. And when we're designing our filter, if we want to magnify things at f1, we'll put poles around f1, and we'll put zeros places we don't want it to be high. So you can imagine this would maybe look something like this. And if we did, say, one pole but zero is very close, we'd get a more narrow response. So the zeros would pin down the response to be close to zero. If we're matching the rubber sheet, we're narrowing it down by putting in zeros. So we have lots of things to play with. This isn't guaranteed to be stable though, right? So if some of these poles are outside our unit circle, it won't be stable. And this is in filter. So the impulse response of this is infinite. There's no way to get a finite impulse response from the system. If we put in a delta function, it would just keep going. It would never stop. An FIR filter, on the other hand, all A's equal 0. So we don't have... No, I'm lost. We don't have this right half. There's no feedback and no recursion. So all we would have left is everything on the bottom. Sorry, everything on the top. So instead of having this, we'd have B naught Z to the M So all our poles for a finite impulse response are in the center. So the nice thing about finite impulse responses is they're guaranteed to be stable, right? So you'll never have an unstable FIR filter. The downside is now you can't play with where you're putting your poles. We can only decide where we're putting our zeros. So we can put, if we want F1 to be high, we can put zeros everywhere else, like this. And we'll get something right near F1. But it won't, we can't design a good as filters if we could play with both poles and zeros. But we have a finite response, and it's always stable. And the downside is our filters aren't behaving as well. So also, if you know that you don't have any recursion or outputs at previous times, you can automatically know that it's a stable system, which is nice. If you're assuming it's casual. So, questions about this? All for filtering. Any other questions about filtering? That was what I had for filtering. Did you want to talk any more about the Laplace transforms? So we have a general filter. We pick the poles and the zeros, we put them where we want them. And that's filter design. Yeah, as I say, if you want to do anything else. How good with regions of convergence? We've got like a tenth of the class here. We can get a good sampling. Although I did want to mention one thing briefly that I noticed on the homework, I guess about entropy, is that we know Huffman, the expected length, if H is the entropy. If this is the expected length, this does not prove that it's optimal. There are other codes that are non-optimal that will also be within this range. This was something I saw some more often than I would have liked. Meeting this condition doesn't prove that it's optimal. There are non-optimal codes. If you looked at the Shannon code, then your homework, that was actually also within this range. So Huffman is guaranteed to be within this range, but it's not.
But I thought it's optimal for like all real-time coding schemes.
It is optimal, but some people are saying that showing that it's in this range proves that it's optimal.
No,
No. No, it's this if it's optimal, but it's not this if and only if it's optimal. It's not an if and only if kind of thing. If optimal, not if and only if optimal. Right, you could have a Huffman that's here and a non-Huffman that's somewhere in between here and not be optimal. It's Huffman. Huffman is the way to get an optimal code. So if you can show it's a Huffman code, then it's optimal. Huffman code
How
was...
do you show it? You set it up as a minimization. Like you can write the expected.
I mean, that's what Huffman is. The whole process of doing Huffman is...
You can write the expected code word length, okay? And subject to Kraft's inequality, which you covered in class, it's a necessary and sufficient condition for decodable code. So you can try to minimize that, and you can like use techniques from calculus like Lagrange multipliers. So if you like take the derivative with respect to the code word length basically, and you'll arrive at the Huffman code.
So doing the Huffman code shows it's optimal. You don't need to reprove that Huffman is optimized. But this does not mean it's optimal. Important. Also, the regions of... I liked the question on Piazza. Someone was asking about the long division. When Professor Cuff divided something plus AZ. Something like that. I forget exactly what he had, but it was something like this, right? And he got a train of deltas multiplied by some constants. Let me see. And so on. We were making an assumption when we started the long division that it was causal. And if we had flipped these, so done like that, we would have gotten something of increasing deltas. Which is non-causal. So the way you set up the long division determines if you get the causal or non-causal response. It's like when we did the partial fractions and there was, if it was non-causal, it has one inverse transform, and if it was causal, it has the other inverse transform. I think it's like minus alpha to the n, you have minus n minus 1, or... And you have to pick one based on whether it's causal or not. So when we do the transform and we determine the region of convergence, the region of convergence always has to go along with the transform. So just saying is not enough. Without the region of convergence. So unlike the Fourier transform where this is enough, it's not enough for the Z and Laplace transforms. You always need to include the region of convergence or you don't actually have a transform. No, I'm done. How do we... Was it F3 or F10? Did you want to say anything else with the homeworks?